Angular displacement. The angular displacement of a particle moving along a circular path is defined as the angle swept out by its radius vector in the given time interval. So as shown in this figure, suppose this is the circular path of the particle. Let's say this is the center of the circle and this is the radius. Okay. Now, suppose initially the particle is at a point P naught. Okay. Now this particle move along the circular path in the anti-clockwise direction. Suppose at a time t1 the particle is at a point A. So this radius now will becomes like this. Okay, and this radius it has covered some angle and that angle is theta 1. Now as the particle moves along the circumference, then at a higher time, let's say t2, the particle now reach at a point B. Okay, reach at a point B, and this radius it becomes like this. So this angle now with respect to the initial positions of the radius vector, it is theta 2, let's say. Now the difference here between A and B, okay, or I can say the angle in which the particle swept between point A and point B, that is between time t2 to t1, okay, between t1 to t2, or I can say during the time interval t2 minus t1, then this particle makes an angle delta theta. Okay, this is delta theta, and this angular displacement, the linear displacement in this case, it is delta s, which is measured along the arcs. Okay, so this arc AB here, it gives you the linear displacement. Delta s is what? Linear displacement along the circumference during this time interval delta t equal t2 minus t1. Okay, now if the radius r here, because it makes an angle delta theta during this time interval, then I can say that this delta theta is equals to delta s upon r. How? Because we know there is a relation, that is angle covered is equals to displacement, or I can say distance upon the radius. Okay, so this delta theta now, which is known as the angular displacement, which is the displacement of the particle during this time interval delta t, that means the displacement from A to B along the circumference is given by this formula. Okay, next, this delta theta, it is measured in delta theta is measured in radian, because angle, it is an angle, so therefore we measure it in radian. Okay, and another point is this delta theta is a scalar quantity. Okay, all right. Next is angular velocity. So we denote this angular velocity by delta by omega only. Okay, sorry. This is not W, this is known as omega. Okay, now how do we define angular velocity? Just like a linear velocity is defined as the rate of change of this linear displacement. So similarly for angular velocity, we define it as the rate of change of angular displacement. So if it is the rate of change of angular displacement, then I can say that the average velocity, the average angular velocity omega, let me write bar, is equals to delta theta, which is the angular displacement, upon time interval delta t. Okay, Just like linear, average linear velocity is defined as what? Displacement, that is delta S upon delta T. Okay, now in case of linear velocity, we have average value and instantaneous value. So similarly, we can define about the instantaneous angular velocity omega as the limit delta t tends to 0 of delta theta upon delta t, or omega is equals to d theta upon dt. So this is what? The instantaneous value of the angular velocity, right? Now this angular velocity, it is measured in, because from the formula it is theta upon time, so therefore it is measured in radian per second. And the dimensions of this angular velocity, it should be only the dimensions of time only, because this radian, it is just the angle, so it is a supplementary unit, so it has no dimension. So therefore the dimensions of omega will be m naught, l naught, and then t minus 1, because second is down, so when you take the time it becomes minus. Okay, right, so this is the dimensions of the angular velocity. Time period and frequency. A time period is defined as the time taken by the particle to complete one revolution. That means, suppose this is a circle. If the particle starts from this point A, it rotates along the circle in anticlockwise. So as it rotates, the time is increasing, and when the particle comes back to the point A, it means the particle has complete one revolution, and the time taken to complete this one revolution is known as time period, and for that we denote by capital T. Okay, so time period means time taken to complete one revolution. Frequency. Frequency is defined as the number of complete rotation in 1 second. Suppose the time is already given to be 1 second. So within this 1 second, how many rotation does the particle can complete? So that is known as frequency. So frequency and time period are reciprocal to each other. So therefore I can say that the frequency, which is denoted by this Greek symbol nu, so nu here is equals to 1 upon t, or I can say t is equals to 1 upon nu. Okay, so this is the relation between time period and the frequency. Next is, let us see about the relation between angular velocity, frequency, and time period. Okay, so by the definitions of time period, we understand that it is a time taken to complete one revolution. Okay, look here. If the particle starts from point A, right, this is the center, as it revolves, then that means the radius r here, it is rotating, rotate. Okay, so as the radius r rotate, and when the radius come back to this point, that means it has covered an angle how much? Because we know from here to here, the angle is pi. Okay, next is how much? Pi. So complete angle in one revolution will be 2 pi. So it means here that when the time t is equals to the time period, the angle theta, which is complete by the particle, is equals to how much? 2 pi radian. Okay, so therefore omega, which is the angular velocity, is written as, we define omega as what? As the angular displacement upon time period. So theta upon t, which means theta is 2 pi, and small t, it is how much? Capital T in this case. Okay, or I can see omega is equals to 2 pi into 1 upon t. Can I write like this? Yes. or omega is equals to 2 pi. Now, what is 1 upon t? 1 upon t is equals to nu. So, I can say that this is the relation between the angular velocity and the linear frequency. Okay.